The National Electrical Code, abbreviated NEC, does not explicitly prohibit the placement of a main electrical panel within 6 feet of plumbing fixtures. However, certain guidelines should be considered. NEC Section 110.26 C1 states that electrical equipment should not be located in areas where it is likely to be subjected to excessive moisture. NEC Section 404.8 A1 requires swimming pools and other water bodies to be surrounded by an electrical safety zone that extends at least 6 feet from the edge of the water. NEC Section 404.8 A2 states that the electrical safety zone may be reduced to 3 feet if the electrical equipment is protected by a ground fault circuit interrupter, abbreviated GFCI. Now let's consider the situation where the main electrical panel is located in a laundry room, where there is a laundry sink. If the sink is less than 6 feet away from the panel, it is important to note the following. Firstly, the laundry sink is not a water body that would require an electrical safety zone. Secondly, the laundry sink is not likely to create excessive moisture that would damage the electrical panel. If an inspector has approved the location of the main electrical panel, this suggests that they are satisfied that the location meets the code requirements. Based on this information, it appears that the location of the main electrical panel is compliant with the NEC. However, it is always advisable to consult with a qualified electrician or inspector to ensure that the installation meets all applicable safety standards. In general, the NEC provides regulations and guidelines related to electrical installations to ensure safety and proper functioning. Firstly, working clearance around electrical equipment is addressed in NEC Section 110.26. It mandates sufficient space for safe operation and maintenance of electrical equipment. The depth of the working space depends on the voltage of the equipment and the conditions present. For instance, condition 1 is where there are exposed live parts on one side and no live or grounded parts on the other side of the working space, or where there are exposed live parts on both sides of the working space that are effectively protected by insulation. Condition 2 is where there are exposed live parts on one side and grounded parts on the other side of the working space. Condition 3 is where there are exposed live parts on both sides of the working space and the operator is required to be in the space between them. Secondly, height of working space is also addressed in Section 110.26. A3. The working space should be clear and extend from the grade, floor, or platform to a height of at least 6.5 feet or the height of the equipment, whichever is greater. Thirdly, dedicated equipment space is found in Section 110.26. It requires that the space above and below electrical equipment be dedicated to the electrical installation. This space should be kept clear of piping, ducts, and other equipment that could interfere with the operation or maintenance of the electrical equipment. Fourthly, access and entrance to working space is covered in Section 110.33. It requires that there be a clear and unobstructed access to the working space around electrical equipment. The access should be large enough to allow personnel to safely enter and exit the working space. Fifthly, illumination for the working space is found in Section 110.26. D. It requires that adequate illumination be provided for all working spaces around electrical equipment. The illumination should be sufficient to allow personnel to safely perform their tasks. Sixthly, protection against physical damage is covered in Section 110.27. It requires that electrical equipment be protected against physical damage. This can be accomplished by locating the equipment in a protected area or by providing physical barriers to prevent damage. Seventhly, entrance of cables and raceways is addressed in Section 312.5. It discusses how cables and raceways should enter electrical enclosures. The NEC specifies that cables and raceways must be properly secured to the enclosure and that any openings must be sealed to prevent the entry of moisture or other contaminants. Eighthly, identification of terminals is covered in Section 110.22. It requires that all terminals be clearly identified to indicate their intended use. This helps to prevent errors during installation and maintenance. Ninthly, interrupting rating is covered in Section 110.9. It requires that electrical equipment have an interrupting rating sufficient for the available fault current at its terminals. This ensures that the equipment can safely interrupt a fault without causing damage or creating a hazard. Finally, available fault current is covered in Section 110.24. It requires that the available fault current be calculated and marked on electrical equipment. This information is used to select equipment with an appropriate interrupting rating. Proper grounding and bonding are critical for electrical safety. The NEC provides detailed requirements for grounding and bonding to minimize electrical shock hazards and ensure proper operation of electrical systems. Firstly, grounding electrode system is covered in Section 250.50. It requires that all grounding electrodes be bonded together to form a grounding electrode system. This system provides a low impedance path for fault current to return to the source, which helps to trip over current devices and clear faults quickly. Secondly, grounding conductor connections are addressed in Section 250.8. It specifies how grounding conductors should be connected to ground in electrodes and equipment. The connections must be made using listed connectors or terminals and must be accessible for inspection and maintenance. Thirdly, equipment grounding conductors are covered in Section 250.118. It identifies the types of conductors that can be used as equipment grounding conductors. These conductors must be sized according to NEC Table 250.122 and must be installed in accordance with NEC requirements. Fourthly, bonding of metal enclosures is found in Section 250.92. It requires that all metal enclosures containing electrical conductors be bonded together to form a continuous electrical path. This helps to prevent voltage differences between enclosures and reduces the risk of electrical shock. Fifthly, bonding jumpers are addressed in Section 250.102. It specifies the requirements for bonding jumpers used to connect metal enclosures and other metal parts. Bonding jumpers must be sized according to NEC Table 250.102 and must be installed in accordance with NEC requirements. Sixthly, sizing of grounding and bonding conductors is covered in Section 250.122. It provides tables and guidelines for sizing grounding and bonding conductors based on the size of the overcurrent protective device protecting the circuit. Seventhly, methods of grounding are found in Section 250.4. It describes the different methods of grounding electrical systems, including grounded systems and ungrounded systems. The choice of grounding method depends on the specific application and the requirements of the NEC. Eighthly, separately derived systems are addressed in Section 250.30. It specifies the requirements for grounding separately derived systems, such as generators and transformers. Separately derived systems must be grounded in accordance with NEC requirements to ensure electrical safety. Ninthly, use of grounding electrodes is covered in Section 250.52. It identifies the types of grounding electrodes that can be used to ground electrical systems. These electrodes include metal underground water pipes, concrete encased electrodes, and ground rings. Finally, resistance of grounding electrodes is found in Section 250.56. It requires that the resistance of the grounding electrode system not exceed 25 ohms. If the resistance exceeds 25 ohms, additional grounding electrodes must be installed to reduce the resistance. Overcurrent protection is essential for preventing electrical fires and equipment damage. The NEC provides detailed requirements for overcurrent protection to ensure that electrical circuits are properly protected. Firstly, circuit breakers are covered in Section 240.83. It specifies the requirements for circuit breakers, including their interrupting rating, voltage rating, and trip characteristics. Circuit breakers must be listed and labeled for their intended use. Secondly, fuses are addressed in Section 240.60. It specifies the requirements for fuses, including their ampacity, voltage rating, and time delay characteristics. Fuses must be listed and labeled for their intended use. Thirdly, coordination of overcurrent devices is found in Section 240.12. It requires that overcurrent devices be coordinated to ensure that the device closest to the fault opens first. This minimizes the extent of the outage and reduces the risk of damage to equipment. Fourthly, standard ampere ratings are covered in section 240.6. It specifies the standard ampere ratings for fuses and circuit breakers. Overcurrent devices must be selected with an ampere rating that is not less than the calculated load current. Fifthly, location in circuit is addressed in section 240.21. It specifies where overcurrent devices must be located in a circuit. Overcurrent devices must be located at the point where the circuit receives its supply and at any point where the conductor size is reduced. Sixthly, protection of equipment is covered in section 240.4. It requires that electrical equipment be protected against overcurrent. The overcurrent protection must be sized to protect the equipment from damage due to overload or short circuit. Seventhly, protection of conductors is found in section 240.3. It requires that electrical conductors be protected against overcurrent. The overcurrent protection must be sized to protect the conductors from damage due to overload or short circuit. Eighthly, interrupting rating is addressed in section 110.9. It requires that overcurrent devices have an interrupting rating sufficient for the available fault current to their terminals. This ensures that the device can safely interrupt a fault without causing damage or creating a hazard. Ninthly, series ratings are covered in section 240.86. It permits the use of series-rated overcurrent devices under certain conditions. Series ratings allow the use of overcurrent devices with lower interrupting ratings provided that they are protected by an upstream overcurrent device with a higher interrupting rating. Finally, supplemental overcurrent protection is found in section 240.10. It permits the use of supplemental overcurrent protection for specific applications, such as motor circuits and appliance circuits. Wiring methods and materials are regulated by the NEC to ensure safe and reliable electrical installations. The NEC specifies the types of wiring methods and materials that can be used for different applications. Firstly, types of cables are covered in Article 310. It identifies the types of cables that can be used for different applications, including NM cable, UF cable, and THHN conductors. The NEC specifies the ampacity, voltage rating, and installation requirements for each type of cable. Secondly, conduit types are addressed in Article 342 through 356. It specifies the types of conduit that can be used for different applications, including rigid metal conduit, electrical metallic tubing, and flexible metal conduit. The NEC specifies the installation requirements for each type of conduit. Thirdly, boxes and fittings are found in Article 314. It specifies the requirements for boxes and fittings used to terminate and splice electrical conductors. Boxes and fittings must be listed and labeled for their intended use and must be installed in accordance with NEC requirements. Fourthly, conductor fill is covered in Chapter 9. It provides tables and guidelines for determining the maximum number of conductors that can be installed in a conduit or box. The conductor fill must be calculated to ensure that the conductors do not overheat or become damaged. Fifthly, support of cables and raceways is addressed in section 300.11. It requires that cables and raceways be properly supported to prevent them from sagging or becoming damaged. The NEC specifies the maximum spacing between supports for different types of cables and raceways. Sixthly, protection against physical damage is covered in section 300.4. It requires that cables and raceways be protected against physical damage. This can be accomplished by locating the cables and raceways in a protected area or by providing physical barriers to prevent damage. Seventhly, use of listed products is found in section 110.3. It requires that all electrical products be listed by a recognized testing laboratory. Listed products have been tested and certified to meet safety standards. Eighthly, wet locations are addressed in section 300.6. It specifies the requirements for electrical installations in wet locations, such as bathrooms and kitchens. Electrical equipment in wet locations must be protected against moisture and corrosion. Ninthly, corrosive environments are covered in section 300.6. It specifies the requirements for electrical installations in corrosive environments such as chemical plants and wastewater treatment facilities. Electrical equipment in corrosive environments must be protected against corrosion. Finally, underground installations are found in Section 300.5. It specifies the requirements for underground electrical installations. Underground cables and raceways must be buried at a sufficient depth to protect them from damage and must be installed in accordance with NEC requirements. Special equipment and systems have specific requirements in the NEC to ensure safety and proper operation. The NEC provides detailed requirements for special equipment and systems such as generators, transformers, and fire alarm systems. Firstly, generators are covered in Article 700 through 702. It specifies the requirements for generators, including their installation, wiring, and overcurrent protection. Generators must be installed in accordance with NEC requirements to ensure that they operate safely and reliably. Secondly, transformers are addressed in Article 450. It specifies the requirements for transformers, including their installation, wiring, and overcurrent protection. Transformers must be installed in accordance with NEC requirements to ensure that they operate safely and efficiently. Thirdly, fire alarm systems are found in Article 760. It specifies the requirements for fire alarm systems, including their installation, wiring, and testing. Fire alarm systems must be installed in accordance with NEC requirements to ensure that they operate reliably in the event of a fire. Fourthly, emergency systems are covered in Article 700. It specifies the requirements for emergency systems, including their installation, wiring, and power source. Emergency systems must be installed in accordance with NEC requirements to ensure that they operate reliably during a power outage. Fifthly, low-voltage systems are addressed in Article 725. It specifies the requirements for low-voltage systems, including their installation, wiring, and overcurrent protection. Low-voltage systems must be installed in accordance with NEC requirements to ensure that they operate safely and reliably. Sixthly, hazardous locations are covered in Article 500 through 516. It specifies the requirements for electrical installations in hazardous locations such as chemical plants and refineries. Electrical equipment in hazardous locations must be explosion-proof or intrinsically safe to prevent ignition of flammable gases or vapors. Seventhly, healthcare facilities are found in Article 517. It specifies the requirements for electrical installations in healthcare facilities such as hospitals and nursing homes. Electrical equipment in healthcare facilities must be installed in accordance with NEC requirements to ensure patient safety. Eighthly, swimming pools are addressed in Article 680. It specifies the requirements for electrical installations at swimming pools, including grounding, bonding, and GFCI protection. Electrical equipment at swimming pools must be installed in accordance with NEC requirements to prevent electrical shock hazards. Ninthly, solar photovoltaic systems are covered in Article 690. It specifies the requirements for solar photovoltaic systems, including their installation, wiring, and overcurrent protection. Solar photovoltaic systems must be installed in accordance with NEC requirements to ensure that they operate safely and efficiently. Finally, wind electric systems are found in Article 694. It specifies the requirements for wind electric systems, including their installation, wiring, and overcurrent protection. Wind electric systems must be installed in accordance with NEC requirements to ensure that they operate safely and efficiently. Electrical safety is of utmost importance, and the NEC provides guidelines for safe work practices. Firstly, de-energizing equipment is covered in Section 110.13. It requires that electrical equipment be de-energized before any work is performed on it. This helps to prevent electrical shock hazards. Secondly, lockout-tagout procedures are addressed in Section 120.1. It specifies the requirements for lockout-tagout procedures, which are used to prevent accidental energization of electrical equipment during maintenance or repair. Thirdly, personal protective equipment is found in Section 130.1. It requires that workers wear appropriate personal protective equipment such as gloves, safety glasses, and arc flash suits when working on or near energized electrical equipment. Fourthly, working on energized equipment is covered in Section 130.2. It permits working on energized equipment under certain conditions, such as when energizing the equipment would create a greater hazard. However, workers must follow specific procedures and use appropriate personal protective equipment when working on energized equipment. Fifthly, approach distances are addressed in Section 130.4. It specifies the minimum approach distances that workers must maintain from energized electrical equipment. The approach distances depend on the voltage of the equipment and the qualifications of the worker. Sixthly, arc flash hazard analysis is covered in Section 130.5. It requires that an arc flash hazard analysis be performed before any work is performed on or near energized electrical equipment. The arc flash hazard analysis determines the potential arc flash hazard and the appropriate personal protective equipment that workers must wear. Seventhly, shock hazard analysis is found in Section 130.3. It requires that a shock hazard analysis be performed before any work is performed on or near energized electrical equipment. The shock hazard analysis determines the potential shock hazard and the appropriate personal protective equipment that workers must wear. Eighthly, job briefing is addressed in Section 110.10. It requires that a job briefing be conducted before any electrical work is performed. The job briefing should cover the hazards associated with the work, the procedures to be followed, and the personal protective equipment that workers must wear. Ninthly, qualified persons are covered in Section 110.1. It requires that electrical work be performed by qualified persons. A qualified person is someone who has the skills and knowledge to safely perform electrical work. Finally, use of test equipment is found in Section 110.12. It requires that workers use appropriate test equipment to verify that electrical equipment is de-energized before any work is performed on it. The test equipment must be properly calibrated and maintained. The NEC is a comprehensive document, and understanding its organization is key to navigating it effectively. The NEC is organized into chapters, articles, and sections. Firstly, chapters are the broadest divisions of the NEC and cover general topics, such as wiring methods, equipment, and special occupancies. Secondly, articles are subdivisions of chapters and cover more specific topics, such as grounding, overcurrent protection, and wiring methods. Thirdly, sections are subdivisions of articles and provide detailed requirements for specific aspects of electrical installations. Fourthly, tables are used throughout the NEC to provide information on conductor ampacity, conduit fill, and other technical data. Tables are essential for selecting the correct wiring methods and equipment for an electrical installation. Fifthly, annexes are appendices to the NEC that provide supplementary information such as examples, calculations, and guidelines. Annexes are not part of the enforceable requirements of the NEC, but they can be helpful for understanding and applying the code. Sixthly, informative annexes provide additional information and guidance, but they are not enforceable requirements. Seventhly, normative annexes are part of the enforceable requirements of the NEC. Eighthly, fine print notes, abbreviated FPN, are used throughout the NEC to provide additional information and explanations. Fine print notes are not part of the enforceable requirements of the NEC, but they can be helpful for understanding and applying the code. Ninthly, definitions are provided in Article 100 of the NEC. The definitions are essential for understanding the terminology used throughout the code. Finally, using the index is a way to find specific information in the NEC. The index is organized alphabetically and provides references to the sections, articles, and tables that cover specific topics. Electrical calculations are essential for designing safe and efficient electrical systems. The NEC provides guidelines for performing electrical calculations to ensure that electrical systems are properly sized and protected. Firstly, calculating load is covered in Article 220. It specifies the methods for calculating the load on an electrical system, including the general lighting load, receptacle load, and appliance load. The calculated load is used to determine the size of the service entrance, feeders, and branch circuits. Secondly, conductor ampacity is addressed in Article 310. It provides tables for determining the ampacity of conductors based on their size, insulation type, and installation conditions. The conductor ampacity must be sufficient to carry the calculated load. Thirdly, voltage drop is found in Section 215.2. It requires that voltage drop be considered when sizing conductors. Voltage drop can reduce the efficiency of electrical equipment and can cause equipment to malfunction. Fourthly, overcurrent protection is covered in Article 240. It specifies the requirements for overcurrent protection, including the size and type of overcurrent devices. The overcurrent protection must be sized to protect the conductors and equipment from damage due to overload or short circuit. Fifthly, grounding and bonding are addressed in Article 250. It specifies the requirements for grounding and bonding electrical systems. Grounding and bonding are essential for preventing electrical shock hazards. Sixthly, motor calculations are covered in Article 430. It specifies the methods for calculating the load on motor circuits, including the full load current, starting current, and short circuit current. The motor calculations are used to determine the size of the conductors, overcurrent protection, and motor starter. Seventhly, transformer calculations are found in Article 450. It specifies the methods for calculating the load on transformer circuits, including the primary current, secondary current, and voltage regulation. The transformer calculations are used to determine the size of the transformer and the overcurrent protection. Eighthly, power factor correction is addressed in Article 480. It permits the use of power factor correction capacitors to improve the power factor of an electrical system. Power factor correction can reduce the current drawn from the utility and can improve the efficiency of electrical equipment. Ninthly, short circuit calculations are covered in Article 110. It specifies the methods for calculating the short circuit current at various points in an electrical system. The short circuit calculations are used to determine the interrupting rating of overcurrent devices. Finally, using software for calculations can simplify the process of performing electrical calculations. There are many software programs available that can perform electrical calculations quickly and accurately. These programs can save time and reduce the risk of errors.